Hello, this is Mr. Henry, and welcome to lesson 0.5, Problem Solving, Rationals versus Irrationals. The essential question says, how do I use rational and irrational numbers to solve problems? So we're using both, and basically this is a lesson on just problem solving, lots and lots of problem solving. Did you know that without square root, GPS could not exist? The way that GPS works is by finding your distance from satellites in space. And some of the math is done and your position can be found. It might be done by the satellites or by your device, your phone or your GPS. And without square roots, they cannot find the distance because there's actually a formula called the distance formula. And it looks like this. Now, this formula will find the distance in a two-dimensional plane, but it can be extended to 3 dimensions, like our real life, up, down, left, right, forward, backwards. It can be extended to 3 dimensions very easily, and it still uses square roots. And so, if you can find your position using your longitude and latitude, it can actually find your position on the Earth very, very accurately. But not without square roots. This lesson does not have any new vocabulary because we are just doing lots of problem solving of the previous lessons. So let's get to it. Example 1, problem solving, says the circumference of a circle can be found using the formula C equals 2 pi r, where r is the radius of the circle. If the radius of a circle is a whole number, would the circumference ever be rational? So if I draw a circle here, and from center to the outside is called the radius, the question is asking if this radius here is a whole number, like 1, 2, 3, 4, 5, would the circumference ever be a rational number? Well, let's try it out. So I'm going to go ahead and erase this little r in here. If I make him, say, a 2, if I start plugging stuff into my formula, C equals 2 times pi times the radius, which is 2 in this case. Now, if I calculator this thing, we get 2 times pi times 2 that is definitely an irrational number. Notice, big ugly decimal, no repeating pattern. That is not rational. Okay, so maybe that's just a bad example. Let's try another one. Let's try with 3. If I put a 3 in here and here, and I take it in my calculator, clear 2 times pi times 3. Irrational again. It's not a coincidence that they're both irrational. It will always be irrational, because this is actually something that we talked about way back, I think, in the very first lesson. We were trying to determine if something was or was not rational. And one of the patterns we found is if you take an irrational number times by a rational number, you're still going to get an irrational answer. It's just going to be bigger. So here, pi is an irrational number. Notice when I was typing in my calculator, I was not using 3.14. I was hitting the pi button. Because if you hit 3.14, it stops. That is not the actual answer. That is an approximation. This, well, heck, that's not even the actual answer. That's also an approximation because my calculator can only show so many digits. To get the actual answer, well, you can't show it all because it's irrational. The numbers go on forever. It's infinitely long and does not have a repeating pattern. Okay? So the answer here is, would your numbers ever be rational? The answer is no. The answers will always, the circumference will always be rational. There we go. Now you can see it. No, the circumference will always be irrational because it's an irrational number times by a rational number. Letter B. One for you to try. It says here, Emily has a square with an area of 35 centimeters squared and a cube with a volume of 85 centimeters cubed. Which of these objects has the largest side length? The length of the side of the object. So what I'd like you to do is pause the video, sketches if you need to, try some stuff out, and figure out which of these has the largest side length. When you're ready to continue, hit play, and we'll go through it together. Alright, so here is, not that, that. Here is Emily's square with an area of 35 centimeters squared. Side length of S. Here is Emily's cube with a volume of 85 and a side length of, well, let's use X, I guess, because we don't know if the S and the X are the same. And we know, is S bigger or is X bigger? That's what the question comes down to. Now, for a square, the area of a square is length times width. In this case, since it's the same, it's just S times S, which is S squared. Now, we know the area. We know the area is 35. It said so in the problem. So if we could figure out what number squared is equal to 35, that will give us how big the length of the side is. Now, square root, because that's the opposite of squaring. That's how you unsquare something. If S squared is 35, if we square root both sides, we get just S equals whatever that is. If I take the square root, second x squared 35 equals 5.916. 5.916. That is how big each side of this square is. And if you don't believe me, if you take 5.916 times 5.916 equals, that is awfully darn close to 35. 34.999. The reason why it's not exactly 35 is because, well, this is not the exact decimal it gave us. This is an approximation. If we use the exact decimal they gave us, with all those digits, it'd give us exactly 35. All right, so the volume of the cube. Volume of a cube is length times, well, width times height. The formula they actually give you, and if you checked out your formula sheet back at the beginning, B equals S cubed. Actually, I don't know if that's on the formula sheet for 8th grade. It's on for 7th grade. Volume is S cubed. Side length cubed. Length times width times height. Now, they tell us here the volume is 85. And we want to know, what is this S? Now, in our problem here, we're not using S. Since we're substituting stuff in, we're using X. So what is X? What number times by itself 3 times is 85? Well, to uncube this, we're going to root sides. That makes these cancel out. And so we get X equals the cube root of 85, whatever that is. So calculator with me if you need to. We're going to hit 3 second caret. That gives us our special root. Cubed root of 85 equals 4.39. So the question is, which of these has the largest side length? Is it 5.916 or is it 4.39? Clearly, that one is the bigger one. So the square has the larger side length, and make sure you say that on your paper. You finally answer the question. Don't just have your work and then stop. Say, the square has the largest side length. Letter C. Mike was doing his math homework when his dog bit off part of the page, taking one of the expressions with it. Mike is trying to fix his homework and remembers that the missing expression was equal to 12 and looked like that. What is the missing number from inside the square root that makes this expression equal 12? So this is going to take either some good problem solving or some good guessing and checking. So let's figure out the bottom here. The bottom is pretty straightforward. What is the cube root of 27? So if we take 3 second caret to get special root of 27 equals 3. Okay. I like where this is going. Because if this stuff here needs to equal 12, then what number divided by 3 is equal to 12? Should be 36, right? 36 divided by 3 is 12. So all you got to do is figure out what x would be here to make this top stuff equal 36. We can use some guess and check, or, well, we can actually probably do better than that. But what would make this top equal 36? Okay, so we know we need this to equal 36. In fact, I'm going to move this over a little bit. I think I can. I think I can. Sure, that works for me. All right, so 4 times what equals 36? I'm kind of working backwards a little bit. I'm trying to narrow down my choices for this x, so I don't just have to start just randomly guessing. Okay, I'm trying to do some problem solving here. So 4 times what is 36? 4 times 9 is 36. 36 divided by 3 is 12. So if I can figure out what square root of what number gives me 9, I'm done. All right, so square root of what gives me 9? You can go back to your perfect square. So, oopsie. You can go back to perfect squares if you need to. There, we have them on one of the previous pages of our note packet. I know it. It's the square root of, square root 81. Square root of 81 is 9. So if this x here was 81, then when I take the square root of it, I would get 9. When I take 9 times 4, I get 36. When I take 36 divided by 3, I get 12. So the answer is, what is the missing number inside the square root that makes this expression equal 12? X equals 1. Problem solving. Not really just, I mean, you could potentially just guess and check. You could try to type this beast into your calculator or this beast in your calculator and put in x equals 1. Shucks, it's too small. And try 2, and try skip it, and try 5, and try 100. And you can try a bunch of different numbers until you get 12. It's probably time consuming. But if you do a little problem solving and work backwards and simplify what you can simplify and try to understand, okay, this top had to equal 36 because 36 divided by 3 is 12, then it helps you narrow down your choices. Hey, that's 4 times by something is 36, so that something has to equal 9. So then whatever this x on the inside is, if I take the square root of it, I have to get 9. Boom. Had to be 81. Letter D. It says, at lunch you counted your M&Ms and found you have 45 of them. You want to use all of the M&Ms to make one of each different sized squares. What size of squares could you make and use all 45 M&Ms? So you want different sized squares and you want to use all 45 M&Ms. Okay, so go ahead and try the problem out. When you're ready to continue, hit play, and we'll go through it together. Okay. So I'm not going to do what I did before in, I guess, the previous lesson with the Skittles problem like this, where I just drug out 36 Skittles. I'm not going to drag out 45 M&Ms. That's going to take too long. But what I know is, since I'm making squares, if I use my perfect squares, those are the numbers that I can make squares out of. So 1 times 1 was 1. 2 times 2 is 4. 3 times 3 is 9. I can make a square using 9. 1, 2, 3, 5, 6, 7, 8, 9. There's the same number on each side. 1, 2, 3, 4, 1. Okay? 1 times 1, 2 times 2, 3 times 3 squared. 4 squared is 16. 5 squared is 25. 6 squared is 36. 7 squared is 49. 8 squared, whoa, 64. I put down the 8, and that's not what I meant. 64. Now, that's too big. I only have 45 M&Ms. So, actually, 49 is even too big. I only have 45 M&Ms. So, using these other numbers, what combination of these guys can make exactly 45? So I'm honestly just looking and doing some math combinations in my head. I'm saying, okay, if I take 36 plus 4 is 40, and then I don't have a 5 here. Okay, so that's not going to work out. If I take 25 plus 16 is 30, 41, and then add 4, does that work out? 4 plus 16 plus 25. A square that has this many, a square of this many, a square of this many. Let's double check our math here. 4 plus 16 plus 25 equals. Hey, that's exactly 45. Now, maybe you didn't see that. Maybe you saw a different one. There's more. The one I was actually dancing around a little bit was, what about 36 and 9? If you made a square of using 36 M&Ms and a square of 9 M&Ms, 36 plus 9 is 45. And who knows, there might be more combinations of them. But the idea here was to understand that using perfect squares, the numbers I have listed here on the screen, using perfect squares can save you a lot of work. Instead of having to drag out 45 little dots or 45 little M&Ms, you know that these are the numbers that can make perfect squares. That's why they're called perfect squares. All right? Letter E. Philip was trying to figure out if the square root of a number is greater than or equal to the cube root of the same number. Give an example of where the square root of a number is greater than the cube root. Also give an example where the square root of a number and the cube root have the same value. Okay. So I guess I'm just going to pick a number. Say 25. I'm going to take the square root of it. I'm going to take the cube root of it. See what happens. So if I take the square root of 25, actually I know that one. Square root of 25 is going to be equal to 5. That's a perfect square. The cubed root of 25, 3-second caret, is 2.92. Give an example where the square root of a number is greater than the cube root. Okay, check. The square root of 25 is bigger than the cube root of 25. Whoops. Okay. Square root is bigger than the cube root. I don't remember what that was. There we go, something like that. Also give an example of where the square root and the cube root have the same value. That's a little bit trickier. Because, I mean, think about it. What times what equals a number? And then what times itself give you the same number? I mean, it can't be like 2. 2 times 2 is 4. 2 times 2 times 2 is 8. That's not going to work. 0? 0 times 0 is 0. 0 times 0 times 0 is 0. I don't know if you can... I mean, I'm not sure if that works. Can you take the square root of 0? Does that give you something weird? Is it a syntax error or something? No? It's a cube root of 0, 0? Whoop, 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 whoop. 3-second cube root 0. Okay. 0 seems to work, right? We plugged in 0 here and here. So the square root of 0 and the cubed root of 0 both give us 0. There's another number that also works. 1. the square root of 1 and the cube root of 1, which I remember we did on one of the previous problems in the previous lessons, these both give you 1 as well. So there's actually 2 examples of where the square root and the cube root give you the same number. Now, apart from these 2 numbers, pretty much every other example you can think of is going to fit into this other category over here, where the square root is almost always going to give you a bigger number than the cube root. Pick any other example you can think of. Square root of 100 is 10. Cube root of 100 is smaller. Oopsie. I did 3 square roots of 100. 3 second caret. Cube root of 100 is smaller than 10. Okay. See how easy it is to make that little mistake? Instead of doing square root, doing cube root, doing 3 times the square root of 100 instead of the cube root of 100. I make that mistake sometimes, and trust me, you will too. Just kind of got to be careful with it. Letter F. Explain in words why you can take the square root of a negative number, but you cannot take the square root of a negative. Why can you take the cube root of a negative number? You cannot take the square root of a negative number. So my example is the square root of negative 64 is undefined, but the cube root of negative 64 is negative 4. So give a thought to that. Try it out. See what happens. When you're ready to continue, hit play, and we'll go through it together. Okay. So, say, what did you come up with? Obviously, did you try it on your calculator? Second square root negative 64. Error. 3 second special root. Oops. 3 second special root. Negative 64. It's negative 4. Okay, so yeah, that gives us an error. That doesn't. Why? Well, here's what it comes down to. So when you take the square root of a number, you get a number times by itself. It's supposed to equal negative 64. And over here, a number times by itself is equal to negative 64. Make it a little bit prettier. Now, it says we know the answer here is negative 4. Negative 4 times negative 4 times negative 4 is negative 64. Negative 4 times negative 4 times negative 4 equals 64. Okay? Check. So what the heck is wrong with this? What number times by itself? Well, wouldn't it be like negative 8 times negative 8? Well, negative 8 times negative 8 is positive 64. If you use positive 8 times positive 8, it's positive 64. You might be thinking, well, can't you just use 8 times by times negative 8 to get negative 64? It is negative 64, but then it's not the same number times by itself. One's positive, one's negative. And no, that's not the same number. Positive 8 and negative 8 are not the same thing. Okay? So the problem is that anytime you take a number times by itself, you always get a positive answer. So there's actually no way to take the square root of a negative number because there's no number, nothing at all that you could plug in here to make a number times by itself equal a negative answer. That's why the calculator gives you that error message. When you try to type in second square root negative 64, the calculator says, hey, it cannot be done. There's an error going on here because there's nothing you can plug in for x. There's nothing you can plug in here that makes a number times by itself equal a negative answer. Okay? It's important to understand that you cannot take square root of a negative number. It's impossible. It's one of those things like dividing by 0. Back in school, teacher said, you can't divide by 0. You can't take 5 divided by 0. Can't be done. 5 divide 0. Error. Can't be done. Calculator doesn't like it. It's kind of like one of those things. You also cannot take the square root of a negative number. That's why in all the previous examples, you might have seen the square root on the outside. That's allowed, because that is the square root of the negative number, and then you throw times by -1. You throw a negative sign in front, and that's okay. You just can't take the square root of a negative number. Letter G. The expression square root of 81 has two possible solutions. What are these two solutions? And show why both solutions work for the square root of 81. Now this kind of comes into play with what we were just talking about in the last lesson. So let's think about this. What times itself is 81? Thinking in your head, you're probably coming up with 9. 9 times 9 is 81. Yes, yes it is. And then I say, well, what else times by itself equals 81? You go, well, nothing else, because 7 times 7 is 49, 8 times 8 is 64, 9 times 9 is 81. We already have that. 10 times 10 is 100. And you can't use something like 27 times by 3, although that does equal 81. It's not the same number times by itself. So what else is there? Well, there is -9 times by -9. These two numbers multiplied by themselves give you a positive answer. That's what I was saying in the last problem we were just looking at. When we were doing the square root of the -64, I showed that +8 times +8 is +64. -8 times -8 is +64. So these are our two answers. Every time you take the square root of a number, well, almost every time, you get two answers. The only time you don't is when you take the square root of 0, because there's no such thing as -0. Now, truth be told, most of the time we ignore the fact that that negative answer exists. Most of the time, we kind of just stick with the positive. I mean, if you look back at the previous examples we did, even in this lesson, here, we took the square root of 25, we got 5. You didn't say, I didn't put -5, although technically -5 is an answer. And over here, I didn't put +1 and -1, although -1 is an answer. -1 times -1 is +1. A lot of the times we ignore that other answer because in some problems it doesn't make sense. Here, we said the answer was 5.916. Well, technically there's also a -5.916 that if you take -5.916 times -5.916, it still gives you +34.999, 35. But it wouldn't make sense in this situation because you can't have a negative side length for a square. It doesn't exist. You can't, sides aren't negative. A length of something isn't negative. Okay? So that's what I'm saying. In a lot of these examples, we ignore the negative, although they exist. And I'm trying to pass the point along that every time you take the square root, you always get two answers. Keep that in the back of your mind. You always get two answers. There's always a positive and a negative of the same number. A lot of times we ignore the negative, but it's still there. So you might see this symbol sometimes. This would be like the square root of 81 is ±9. It's either a +9 or a -9. It could be both or either. So you might see that symbol used. It's a plus sign and a minus sign, or a positive and a negative. So number, square root of 64 is +8 or -8. Letter H, and I don't know why there's a little line hiding. Oh well, guess he's stuck in there. Letter H says, square A has side lengths of 4 square roots of 8, and 6.4 repeated. Square B has side lengths of 9 cube roots of 125 and square root of 64 over 6. Which square has the greater area? The only hint I'll give you before I have you guys try the problem on your own is, just in case you don't remember the area from a formula for a square, area equals length times width. By 8th grade, you should know this, but there you go. Merry Christmas. So if you could, please pause the video, try this problem right now, figure out which of these squares has the greatest area, and we'll go through it when you are ready. All right, so square A, square B. Square A has side lengths of this and this, so 66.4 repeated was on one side and 4 square roots of 8 on the other. Notice how I like to draw my pretty pictures. Square B has side lengths of 9 cube roots of 125 and 64 over 6. All right. So basically, I'm going to evaluate this, change them all into decimals, and then take length times width for square A to get the area. Take length times width for square B, get the area. Let's do. I really don't need to mess around with the 6.4 repeated because it's already a decimal, but I'm going to change this one here. So the 4 times the square root of 8 is 11.313. 11.313. Check. And actually, I'm going to round that 3 up to a 4 because the number next to it is a 7. It's bigger than it's 5 or bigger, so it's always good rounding habits. All right, so I've got 6.4 and 11.313. So if I multiply them together, area equals length times width, 11.314 times by 6. I'll throw a couple decimals in there. 444. What does that give me? 11.314 times 6.444 equals, my area is 72.907. So I know the area of square A. Square B is length times width. All right, so I need to figure out what these two guys are as decimals as well. Now, I can actually do some of this one by myself because I know the square root of 64 is 8. And then 8 divided by 6 will be a lot easier to type in. 8 divided 6 equals 1.3 repeated. Okay, 9 cube roots of 125. So I'm going to do the cube root of 125 first, which actually I know off the top of my head, but 3 second caret to get our special root. 125 is 5. Then I'm just going to hit times 9. I'm going to take the cube root of this times by 9, and that gives us 45. So this side has a length of 45. This side has a length of 1.3 repeated. So if I plug them into my formula, 45 times by 1 point, and I'll throw a couple 3s in there, just like I did for the 4s. The 6.4 repeated, I put a couple digits in there. It makes it a little bit more accurate the more digits you include. 45 times by 1.333 equals 59.985. 59.985. So now the question is, which square has the greater area? The answer is, well, square A. Square A has the greater area because 72 is bigger than 59. It's easy as that. So we changed everything into a decimal. We then plugged it into our formula and let the formula do the work for us. But that decimal part was key because that makes it much, much, much easier to type into the calculator. You don't have to worry about, is the calculator doing the problem right when you have decimals. If I try to type in 4 times the square root of 8 times 6.4 repeated, there's a chance the calculator may not understand what I'm doing. It wouldn't do the order of operations properly. Okay? Letter I. Which two integers fall between that and that. So what I assume they're talking about is on a number line. Somewhere I have, and I don't actually know what the values of these two are, but let's just play pretend that this is the smaller one. Somewhere I have like negative the cube root of 30, or square root of 36 over 3, and the cube root of negative 125. And in between here, I actually have some integers. Some numbers like negative 2, negative 3, negative 4, negative 5 are in between here somewhere. And that's what it's asking. Which two integers, positives and negatives, no fractions, no decimals, are between here and here? So the first thing I got to do is I got to figure out what these two values are. So I'm going to do this one first, since I actually think I just did this problem in the last example, didn't I? Yeah, cube root of 125, it's 5. So this cube root of negative 125 is negative 5. Over here, the negative square root of 36 divided by 3. So I know I'm going to get a negative. I know the square root of 36 is 6. Divided by 3, that's negative 2. So actually, if I look at it, my number line is backwards, because negative 2 is bigger than negative 5. So I need to move these things down this way, him over here. And I'll move the corresponding pieces up top as well. This, there. Because negative 5 is smaller, negative 2 is bigger. So now the question was, what two integers fall between here and here? Well, what's between negative 2 and negative 5? Well, we've got a negative 3, negative 4. Those are the two integers between those two values, negative 3 and letter J says Daniel needs to match up each rational number with its decimal equivalency. Help Daniel by drawing lines from each rational number to its decimal expansion. Okay, so this is going to be a problem for you to do. You're going to match the numbers on the left with the corresponding value on the right. Which ones are equivalent? So go ahead, pause the video, try the problems on your own, match them up. When you're ready to continue or you get stuck, hit play, and we'll go through them together. Okay, so first thing I would recommend you do is take all these things and change them into decimals. That's the easiest way to compare sets of mixed, ugly types of numbers. So I've got some decimals, I've got some fractions and mixed numbers and square roots. But if you change everything into a decimal, then everything looks alike. So he's good, he's good, he's good. I'm going to start with this. 8 times second square root of 25, which, by the way, the square root of 25 is 5. 5 times 8, it's going to give me 40. Now, with just that, I can already match up. I know that this matches up with that. If this was equal to 40, that was equal to 40. Over here, start doing. Now, there's some that you might be able to do in your head. Hopefully, by now, you know what 1/4 is as a decimal. It will be 0.25. So we can say this guy and this guy are a match. I'm going to do the top. 88 divided by 9 is 9.7777. I think there's a typo in there. Well, how about this? Let's do 1/8. Let's try this one. 8.18 and 1/8. That's 0.125. So 8.125. So this guy matches up here. So let's do a little problem solving. So what should this actually be to make it match up with that? Well, it should be 8 and 8/9. Looks like somebody made a boo-boo when they made this problem up. 88/9, as we saw, 88 divided by 9 is not 8.8 repeated. But 8 divided by 9 is 0.888888. So this should actually be 8 and 8/9. So if you tried that problem and you saw it wasn't matching up, good for you. And if your notes are already fixed by the time you get here, as I redo this video later on in the future, great job. It should be 8 and 8/9. Example 2, multiple choice. A square has an area of 50 centimeters squared. What would be the perimeter of this square? Round your answer to the nearest thousandths. What would be the perimeter of the square? Okay, so a square has an area of 50 centimeters squared. I want to find the perimeter. So, a square has sides. The sides are the same. To find the perimeter, in case you don't remember perimeter, the perimeter of a square, if you take and you add all the sides together, so this plus this plus this plus this, you add all 4 of them together, and that would give you your perimeter. So the real problem here is, if I could find out how big the side length of my square is, then I would just plug that number in here, and bada bing, we got ourselves an answer. So how do I figure out how big each side of a square is? If this guy has an area of 50, how big would each side be? Well, think about this. Let's imagine I had 50 little Skittles in here. I can't actually draw it out, but imagine I had 50 little Skittles in here, all forming a square. How big would each side of that square be? You're going to see it doesn't work out exactly, right? The closest thing would actually be 49. If there was 49 Skittles in here, then each side would have a length of 7. 50 is not a perfect square. If I take the square root of 50, it gives me that. So S is 7.07 side. And so a lot of people go, oh yes, the answer is B. No, it's not. Not even close. The question was not how big is one side. The question is, what is the perimeter? What would be the perimeter of the square? Don't just jump for the first answer you see as you type something into the calculator. Finish the problem. Okay? The length of one side of this square is 7.071. Now, some of these other answers. If you took this 7.071 and said, okay, this plus that, you add it up. 7.071 plus 7.071. 14.142. And you're looking, oh God, I don't see that answer here anywhere. Good, because that's not right. The problem here is that some people, when they try to find the perimeter of their square, instead of adding all 4 sides, like you should do, they only add the 2. This is only half of the perimeter. You only added 2 of the sides of the square. You need to add all 4. So if you double that. If you take that times by 2, 28.284. Do we see that somewhere? Yeah, we do. Right there, letter C. That is the perimeter of the square. Okay? Now, I can tell you how these other answers, the other wrong answers came about. So let's imagine this. Some people might take this 50 and then divide by 2. Get 25. Or they might take it and they divide by 4. Actually, I think that's a more common answer. They divide by 4 and they get, well, 12.5. They go, oh, yay, letter D. No. And they might take that 12.5 and they add it together 4 times, times it by 4, and they take 12.5. Actually, it'd be 12.25, I think. Times by 4, and they get 50. They go, oh, yay! No. Because this is an because this is not a perfect square, when you take the square root of it, it gives you a non-perfect answer. Or you could think of it another way. Since this is not a perfect square, you know that the side lengths are not going to be perfect answers. They're going to be irrational decimals. Summary. So, all I want you to do is list 3 things that you've learned about rational and irrational numbers in the past 5 lessons. You should be able to make a list of probably 10, 15, 20 things. I'm only asking for 3. 3 things that you learned between when we started this unit and now. So you can go ahead and you can pause the video and do that on your own. This has been lesson 0.5. Thank you for watching. Bye-bye.